Today we're looking at the applications of using the redox table and using half reactions. So it says for a zinc and gold oxide cell in the solution of potassium hydroxide, determine the oxidation and reduction half reactions. So that's the first thing we're going to do is determine the oxidation and reduction half reactions. So step 1, we need to find appropriate reactions on the table of standard electrode potentials. Okay, so what do we want? We want zinc, because they gave us the full zinc, so we need zinc, and we need gold 3 oxides, so we need gold, and gold's formula is Au. Okay, so we go down, we find zinc over here. Okay, and if we keep going down, we find Au3 plus over there. Now, I know that this table is incredibly small for you guys, and I apologize about that. What I'd like to suggest you do is that, as I say all the time, you really should have your formula sheets and your redox tables and everything with you whenever you are doing science, whether you're watching a video on it or studying it or whatever. So I would suggest that you make a plan to have your redox table, whether in the textbook or on your notes, with you so that you can go through these examples with me. Okay, so it says find appropriate reactions on the table of the standard electrode potentials. Done. Okay, then it says step 2, determine the electrode potential for each of the metals. So do you see that the zinc's half cell has an electrode potential of minus 0.76, whereas gold's has got, Au's half cell has got a positive 1.50. So what does that tell us? That tells us which one is going to be oxidized and which one's going to be reduced. I'm going to circle them again so that there is zinc and Au here is down here. Okay, so we know that the zinc has more negative EMF. Therefore, gold is more easily reduced. Let's put it this way. Since it's more positive, it is more likely to attract the electrons. So therefore, it is more likely to gain electrons. Because remember, oxidation is loss, reduction is gain. Oxidation is loss, reduction is gain. So the reduction half reaction and the oxidation half reaction. So let's think about this. We've just said that this is going to be the oxidation half reaction, and this is going to be the reduction half reaction. And remember, guys, yesterday I gave you a clue. I said, if you can draw it, you're using table 4B. Everything that I teach you about the tricks and things is using table 4B. Okay, there are 2 tables on your formula sheets, 4A and 4B. I would suggest that you use table 4B simply because this actually works for it. So we started with some zinc. Okay, there's our zinc. We added it to gold ions. There's some gold ions over there. So if you look at it, we went from zinc to zinc 2+ ions. Then we went down, and then we went across. Okay, so what we're saying is that if you can draw a C with the reactions, then we know it's spontaneous, and it works as an galvanic cell, a galvanic cell. So the oxidation reaction is the one that is losing electrons. So it's going to be zinc goes to zinc 2+ plus 2 electrons. And please, grade 12, note that now your arrow is in one direction, okay? Whenever you're drawing them over here on the redox table, you see that the arrows go both ways, and that's because these reactions can go both ways. It can either be zinc 2+ plus 2 electrons goes to zinc, or that zinc breaks up into zinc 2+ and gives off 2 electrons. But in this case, we know that zinc is being oxidized, so it loses some electrons, 2 electrons to form zinc 2+. At the same time, your Au 3+ is gaining 3 electrons to form gold. Okay, that's what's happening. We're getting gold out. So the Au is forming gold. Right, so let's carry on. And I've said remember oil rig. Now step 4 is compare the number of electrons in each equation. So you can see that here there are 3 electrons and here there are 2. So do you agree that I could multiply the top line by 2 and you could multiply the bottom line by 3 and we'd end up with the same number of electrons, okay? This would be 2Au3 plus 3 times 2 is 6 electrons plus 2Au. This is 3Zn plus 3Zn2 plus goes to 6 electrons. So then if you balance it, you get 3Zn plus 2Au3 plus 6 electrons, but that cancels with that. So it goes to 2Au plus 3Zn2 plus. Okay, right, so there we've balanced it. Now, it says a combine equation into one. Okay, so before we carry on, I just want to talk to you about writing this in the specific notation, in the cell notation. So let's say, how would you write this in the cell notation? So I don't know if you remember, but the cell notation worked like this. It was the anode, then the anode's electrolyte, the salt bridge, the cathode electrolyte, and then the cathode. Okay, in that order. So the only time it doesn't obey that order is when you have the hydrogen half cell, in which case the hydrogen half cell, no matter which way it's working, whether it's working as an anode or cathode, the hydrogen half cell is always on the left-hand side. Okay, always. So the way we would write this is, we said that we know that anox and a red cat are important in the section. So reduction occurs at the cathode and oxidation occurs at the anode. So this is the anode reaction and this is the cathode reaction, right? So therefore, what do we have? We've got zinc going to zinc 2 plus. So we've got zinc going to zinc 2 plus, salt bridge, and then we got Au 3 plus going to Au. And now you don't have to write the coefficients that balance this reaction. Okay, have we finished this? No, we haven't, because what you always have to write, 1 mole per decimeter cubed. You always have to tell them that this is happening at a concentration of 1 mole per decimeter cubed in order to ensure that you actually get out these E theta values. Okay, if you don't do that concentration and at the same standard temperature and pressure, you will not get out these specific EMFs.